Okay, let's recap what we've seen so far. So we've been talking about homology. And at the beginning of a discussion of homology, we had introduced simplicial homology. Simplicial homology. And with simplicial homology, we can calculate lots of things. The things I'll be interested in right now are the homology groups of the spheres. So, let's say we have S0. Okay, you remember what S0 is? S0 is just 2 points. Or maybe that was a little bit uninteresting. We could do the simplicial homology of S1 or the simplicial homology of S2 and so forth. You tell me what are these homologies? Like, what is the homology of S1? What's the homology of S1? It's Z when n is 0, and it's Z for n equals to 1, and it's 0 otherwise. Okay, how about for 2?
0.
Yeah, it's again, n equals 0, it's Z. We actually showed that whenever it's path connected, it's going to be Z for n equals 0. And then you also have a copy of Z at n equals 2. And it's just 0 otherwise. In general, Hn of Sm is of the form Z if n is 0, and Z if n equals m, but 0 otherwise. Except here, S0 is kind of this weird special case. So what is S0? Remember, S0 is just two points. It's the boundary of an interval. So it's just the 2 points, 2 endpoints. And so what does that come out to be?
Z squared.
Yeah, you get a Z squared for n equals 0 and a 0 otherwise. Okay, so this is the homology of the spheres, generally of this form, except in the special case when m is 0, you just get a Z squared here. These collapse to give you a Z squared. And you can calculate this quite straightforward with simplicial homology, right? And we talked about how to do this thing. We did some of these examples when doing simplicial homology. Now, when we move to singular homology, we know secretly that singular homology is equal to simplicial homology. I've alluded to that. I think I've even said it. We haven't justified it. So secretly, it should be the same. But the only thing we've shown so far is the first one. Because if you recall our result for singular homology, we said that H0 of some space x is going to come out. Do you remember what this was? Well, it comes out to be Z if it's path connected, and if it's several separate spaces, if it's a disjoint union of path connected spaces, it's just Z to the k if x is the disjoint union of k path connected spaces. Path connected spaces xi. So we've shown this for singular homology. That was like 2 lectures ago, I believe. So that would give us this first result, right? What I want to do today is I want to justify this for singular homology. So we're going to prove this today for singular homology. But before I do that, so far we've done these all for simplicial, but we've only done the first guy for singular. Only from direct results from singular homology is the first one. But before we do that, I want to point out that this is kind of awkward. That this convention of having that H0 of a path-connected space y, if y is path-connected, for y path-connected, by having this a copy of Z, that comes out to be quite awkward. Because here you get all of these like extra Z's in the n equals 0 case. And it kind of makes sense that you might just want that like Hn of S2, it's just Z for n equals 2. These extra Z's seem to kind of be just like an extra feature laying around. And here you're going to have 2 of them, It's like, it'd be nice if it was just 1. Like, it'd be a whole lot nicer if I didn't have this z, if I didn't have that, if I didn't have this z, if I didn't have this z. It'd be a whole lot nicer if this was equal to 0 for a path-connected space. It would just look cleaner, right? It would look nicer. So it would be nicer if these were all zeros. And so what I'm going to do is I'm just going to slightly alter my definition of homology, where I'm going to introduce what I call reduced homology, where reduced homology will just kill off, I'll denote it with this tilde, just kills off a copy of z for n equals 0. So I define reduced homology as follows. Reduced homology, which will be denoted hn tilde of x, will be exactly the same as singular homology. So this is reduced homology. They're exactly the same for all n except for n equals 0, where your reduced homology has 1 fewer copy of z's. So you kill 1 of the copies of z from regular homology. The reduced homology has 1 fewer copy of z for n equals 0, but otherwise it's exactly the same. And it just turns out that this is a convenient bookkeeping feature. So we'll have a result today, and the theorem will look quite nice when we write it in reduced homology, and it wouldn't look nearly as nice if we didn't do this little move. And this is much nicer to state now. You know, what's the reduced homology of the sphere? Well, it's equal to z when n is the dimension of the sphere, and it's 0 otherwise. Much cleaner result. Are we okay with that little revision? Okay, so nothing significant, is just a bookkeeping convention to make a homology a little bit cleaner. Note, one nice feature of reduced homology is if I have Hn reduced homology of some space x, where x is contractible, then what does this come out to be? Yeah, so recall, we proved last class, this was our theorem of the last class, if x is homotopy equivalent to y, then they have the same homology. For all n. And you could change this to reduced homology, that would still be the case. Because in reduced homology, you're removing a z from both of these for h0. But if your space is contractible, then it's homotopy equivalent to what? Just a single point. And the homology of a point is, well, z, 0 is everything except for at 0 at z, but the reduced homology is just 0 for everything. So now it's just 0. We don't have to have this exception, oh, it's 0, it's z in the case n equals 0. No, it's just 0 for all n. For all n greater than or equal to 0. So I'm kind of trying to show you, like, working with reduced homology just makes our statements a little bit simpler. We don't have to worry about the weird things happening at 0. Good? Yeah? Okay. Well, I need to introduce us to some new algebraic tools today. Before we can prove this result about spheres, I need to introduce us to an algebraic structure, a very important algebraic structure. And so by way of motivation, let me remind you that when we defined homology, we have these chain complexes, where a chain complex is just some groups, Cn plus 1, for your space, x, in the case of a chain complex, maps to Cn of x. You have your boundary map, maps to Cn minus 1 of x with another boundary map, and this continues forever. If you want to, you can specify this is the boundary map n plus 1, and this is the boundary map n. And the defining feature of chain complexes we saw was that when you compose two boundary maps, so if I first take the boundary map n plus 1, and then I take the boundary map n, I come out to get 0. This is the same thing as saying the image of the boundary map of n plus 1 sits inside of the kernel of the boundary map for n. Right? So that was kind of a key feature. And this is how we can define homology, because we just defined Hn to be this kernel mod out by that image. And you can mod out by because we're in a abelian group, so it's a normal subgroup. Right? So that's what we had defined. What I want to introduce us to today is a sequence where I'm going to follow this basic format. I'll just generalize it to some group an plus 1. We'll talk about what these groups can be in a minute. But I want to write it in general first. Some sequence that looks very similar. And it continues on as far as you want. And it has some maps between them. Not necessarily boundary maps. I mean, these aren't necessarily cell complexes. This could be whatever. So this could be just a map. I'll call it alpha n plus 1 alpha n. Here's an alpha n minus 1, so forth. So sequence could be finite or infinite. We'll look at some examples today here in a minute. A sequence that has the property where I don't only have the image of alpha n plus 1 being inside of the kernel of alpha n, rather I'm going to have it equal to the kernel of alpha n. So it's still the case that if I compose these guys I get 0. It's still the case that alpha n composed with alpha n plus 1 comes out to give me the 0 map, but something stronger is true. The image of this map is exactly equal to the kernel. So everything that gets sent to 0 was the image of something here. So like thinking through what this means, it says if you have some a that maps to 0, then that a is the image of something, where this is your map alpha n, then that a is the image, must have been the image of something back here. B, that's kind of a weird notation. But if your a maps to 0, then a must have been the image of something. Okay. We're going to call this an exact sequence. So let's look at some properties of exact sequences. So let's look at some basic examples. Suppose we have an exact sequence that has a 0 in it, and then has some a is some abelian group, whatever it is, has some b, and then it goes to 0. And we'll have just one map between these guys. I mean, there's a map from b to 0 as well. It's just the 0 map. That's not very interesting. And there's a map from 0 to a as well, just including 0 into a. So this is not a very interesting map either. You're just including the 0 into a, kind of a dumb map. But if you have this exact sequence, what does that tell you about a and b? Well, let's apply this property. The kernel of a, the kernel of this map alpha should be the image of this map, right? What is the image of this map? Just 0. So the kernel of alpha is 0. What does that tell you? If this is some map from some group to some homomorphism, you have a homomorphism from A to B, and the kernel of it is 0, what does it tell you about alpha? No, you just have that alpha is injective, right? If the kernel is 0, that just means it's injective. That's right. So you can think of this copy of A living inside of B. Alpha A is something in that alpha A is isomorphic to A, right? But you just have A injects into B. But now we have a second two maps we can think about, where this property says the kernel of this map should be the image of this map. So the image of this alpha should be the kernel of this map. What's the kernel of this map? Everything. So what does that tell you? If the image of alpha is all of B, what does it tell you about alpha? Alpha is surjective. And now it's putting these together that you conclude alpha is in fact an isomorphism. That A is isomorphic to B. So if you have an exact sequence, whenever you have zeros, and there's just two groups between those zeros, it being exact is the same as saying A is isomorphic to B. Okay. What if you have three groups coupled between zeros? There may not be zeros at all. You know, we will see some exact sequences where there are no zeros at all. But the way this often will play out for us is we'll get some zeros and that'll help us solve things. So it may be the case that there are no zeros, but let's think about this guy. This is called a short exact sequence. It's we'll see it pop up time and time again. Well, you'll start off with 0 mapped to some A, maps to some B, maps to some C, maps to 0. And I don't know what these maps between are. I'll just call him alpha and beta. And this is just taking that 0 into A, and this is the 0 map over here, right? So these are not very interesting maps. But let's see what we can say about this. So again, what can you tell me? Knowing this is exact, what does that tell you? Good. So once again, just like before, you still have that alpha is injective. And here, just like before, you have your beta now is surjective. I think that's it. Here you have, the middle one here tells us one more thing that's of note. We could also write this down. The image of this alpha is the kernel of this beta. Okay. So this may be a fact that I don't know if you've learned this or not in your abstract algebra class. I imagine you did. If you have a homomorphism from B to C, then I claim that C should be isomorphic to B mod out by the kernel of beta. Is that something you guys talked about? Does that sound familiar? Yeah? Okay, very good. I'll give you a concrete example of this in a second. But let's think about what that means in this setting. What is the kernel of beta? It's the image of alpha. So this is isomorphic to B mod out by, well, it is actually equal to. It's actually equal to just the image of alpha. What is the image of alpha? Well, alpha is injective. So alpha being injective means that the image of alpha is isomorphic to what? Just a copy of A. That's exactly right. So this is isomorphic to B mod A. So maybe this can now motivate like a concrete example. I'll give you an example from algebra. The last guy, C, should be B mod A. So think about something like mod something. It could be something like Z mod 2Z, which means here you should have 2Z, and here you should have Z. Okay, let's think about what all these maps are here. So this map's dumb, just including 0. What is this map from 2Z to Z? Yeah, this is just the inclusion map. So I'll denote it by I, but you're exactly right. This is just going to be inclusion. So for example, 4 will just map to 4. Okay, how about this map from Z to 2Z? Yeah, this is just modding. So I'm going to call this the quotient map. So it's a kind of quotient map But really what it's doing is it's just looking at it mod 2. So if you had a number like 7, it would just map to 7 mod 2, which is 1. Okay, so this is like kind of a canonical example of a short exact sequence. And you should check, that these properties hold. So, we claimed that this alpha is injective, and it's like, sure enough, that's injective. And we claimed that this beta is surjective, and like, sure enough, that's surjective. And we claimed that the image of alpha is the kernel of beta. What is your image of I here? Let me get a new color. What is your image of this inclusion map? Yeah, you can think of it as 2z. But absolutely then, that would be the kernel of this quotient map. Because those are the things that get sent to 0 when you do mod 2. 2, 4, 6, 8, so forth. Okay, so this is a short exact sequence. So this is what you should have in mind whenever we talk about short exact sequences. And there's nothing special about the number 2. You could do 3 instead, Okay, so that is a short exact sequence. So why are we talking about exact sequences? We're talking about them because we have a theorem, or why we're talking about exact sequences more generally. We're talking about them because we have a theorem that says that homology, here I'm talking about singular homology, reduced singular homology, forms an exact sequence. So singular homology groups form an exact sequence. Form an exact sequence as follows. So here's my theorem. If A is some subspace in the space X, then there exists the exact sequence that just maps the nth homology group, reduced homology group of A into the nth reduced homology group of X into the nth reduced homology group of X mod A. So far you should think this kind of looks like that exact sequence we just talked about. The A, the X mod A, except these are spaces, and so you need to turn them into groups, so homology is turning them into groups. And then it continues, Hn minus 1 of A to Hn minus 1 of X to Hn minus 1 of X over A. And then it continues ad infinitum. So, this always keeps going. As high as you want. Okay. Let's talk about the maps. What would be a natural map from A to X? The inclusion map. And so here, we will just say it's whatever the inclusion map induces on homology. So here, I is the map from A to X achieved by inclusion, and this is just the induced map on homology. What's the map from X to X over A? Quotient. So this is the induced map of quotient. So Q is just your quotient map from X to X over A. This is just your quotient map. Now there's one more map from x over a to a, but you're going to be moving from hn to hn minus 1. I'm going to denote this by boundary. And for boundary, it's mysterious. I'm not going to define it today. We'll come back and talk about it. So we're not going it's going to take some construction to understand what this boundary map is. So we'll come back to this. So stay tuned. Maybe that's better than mysterious. Stay tuned. The theologians appeal to mystery. We appeal to the future. Stay tuned. Okay, we'll come talk about what that is. Maybe you should play around and kind of think like, what does an element of this group look like? And what is something kind of like taking boundary that takes you to A? So this is a nice thing for you to think about. You can think about that, but we'll come back and define that in the future. We actually don't need to know what it is for today. But I claim that once we know this theorem, if you accept this theorem, we're not going to prove it today. We're just going to show what we can do with it. If you accept this theorem, we can use it to start calculating homology. So I'm erasing pretty much the only thing we know so far. We only have 2 facts about singular homology really that we've shown at this point. I guess you could reduce it to 1 fact. All we've shown is that the singular homology of a path-connected space is, the singular homology of a contractible space is 0 if you're doing reduced homology, which is 0 for all groups, right? It's contractible, it's 0. And then the special case of S2, well, it's 2 points, and so it comes out to give you 1 copy of, of S0, sorry. So let me just say what we know. So singular homology. Singular homology. I believe all we've really proven, okay, maybe a couple other things. 1, we've shown that any HN, reduced homology to get rid of that special case of 0, for a contractible space is 0 for X contractible. And then the other one is like, what is HN of some, well, I'll just do like S0 as the key example. Of S0, well, your 0 would give you 2 components, but 1 gets deleted because this is reduced. So this is just Z for n equals 0 and 0 otherwise. These are the examples we've done with singular homology. What I want to do now is I want to prove, it's a proposition, that the singular homology for some sphere Sm, for any dimension m, any non-negative dimension m, will just come out to be a copy of Z when m equals n, or I should say when n equals m, and 0 otherwise. That's what I want to prove. Which you already know is true, but we actually want to prove this now for singular homology. We know it's true in simplicial homology. Okay, so you tell me, how could this possibly be helpful to prove this fact about spheres? Well, I guess we want to try and think what is some quotient that is related to spheres somehow in some spaces like X and A? And really we can only talk about contractible spaces. So, what can we say? So there's some contractible spaces that you quotient out somehow, or get some relationship between a contractible space and the spheres. And I claim there is such a relationship. In particular, if I take my space X to be the disk, and I take A to be the boundary of the disk, which is just a m-1 sphere, then When I quotient out by the boundary, what do I get? What do I take if I get like a two-dimensional disk and I quotient out by its boundary? What does that become? Well, this just becomes a two-sphere. Right? This was D2, and I'm quotienting out by its boundary, which is a copy of S1. And that just becomes an S2, where that whole boundary gets like squeezed to a point on the North Pole or whatever, right? You pull the boundary up to a point. So we have here that dm mod out in general by Sm minus 1. You can think about higher dimensions, a little more tricky. You do that. Comes out to be just Sm. Okay, so let's see what we get when we plug this in to our exact sequence, nice long exact sequence. So, you know, let's just start plugging it in. So I'll have Hn of A, Sm minus 1, will get included into Hn of X, will get included into the quotient Hn of Sm. And okay, these are all reduced. So if I forget to say these are reduced, they like the little party hats, you know? He should then go to Hn minus 1 of Sm minus 1. And he should then go to Hn minus 1 of Sm minus 1. And he should then go to Hn minus 1 of Sm minus 1. And again, you know, there'll be another map, and just like here, there's another map. Another map.
D and S.
Thank you. Let's make sure we did this right. This is D, this is M, this is dm, and that's Sm. Okay, yeah. These are not changing. This is just your spaces are staying the same. So this is good. This is my space A. This is my space X. This is X over A. Looks good now, right? Okay. What homology groups do you know here? Good. You know your dn's are just the homology of any contractible space is just 0. So these are just 0. So what jumps out at you? 0, something, something, 0. So just like we saw here, well, I erased it. Yeah, when you have just 0, something, something, 0, you get that this guy is isomorphic to this guy. So we conclude that Hn of Sm is isomorphic to Hn minus 1 of Sm minus 1. Is that good? Okay, and then so what you do is, since you know what it is for, so it's like, what is the homology of S0? You know the homology of S0. It's like, I know what my homology is of S0. It's just identically, well, not for the, it's a copy of Z for n equals 1, n equals 0, and it's 0 otherwise. And then what that identity tells me is I can now figure out what is the homology of S1, right? It's like, well, my S1 will be the same as my S0, but I have to shift the homology groups by 1. So that Z goes from being at n equals 0 to being at n equals 1. So I get a Z at n equals 1. And I know that n equals 0, he's 0 because he's path connected. So that one I know. And then it's 0 otherwise. And then, etc. You know, by induction, you just keep bootstrapping it this way, and you get that you're going to have a copy of Z when n equals m, and it's 0 otherwise. That's what we've proven. Is that good? Notice in this analysis, we didn't even need to know what these maps were. That's why I didn't take time telling you about this map. In the future, I will, but all we need to know is it's 0, and therefore these two have to be isomorphic. Sometimes we'll have to analyze them thinking carefully about what the maps are. But when you have zeros on the end of two things, you just know they're isomorphic. And that gave us what we needed to get the result. So this is quite nice. But it turns out this is a special case of a more general effect. So Hatcher has this more general effect as a problem assigned in the end, but I think it's worth mentioning it because it's a nice little effect. Shows us the power of this kind of argument. So let me remind you some terminology. If you have some space X, you can get the cone of X, which is denoted C of X. What this is it's just X cross the interval. So maybe I should write, it's X cross the interval, 0, 1, where you collapse one end. So I'll say like, I collapse X cross 1. So for just a really crude schematic, let's think of X just being like a copy of S1. Then the cone of X, you should think, is you cross this with the interval. But then I collapse it by the top. So when I take that quotient, I end up with the whole top becomes just a point. And I have something like this. That's called the cone of a space. And you don't have to do S1 of anything. So you're thinking you're popping out to another dimension and then pulling it all down to a point. The suspension of X is defined by doing the same thing, but at both ends. So you could think you take X across the interval and you quotient both ends, or at this point, since you already have a cone, you think it's the cone, just quotient at the other end now. So typically it's written the interval suspend both ends, but since I've already gotten the cone, I'm just going to think of this as the cone of X, where now I suspend this other end. Okay, so maybe suspend by the collapse the copy X at the bottom. You could think of it this way. You could think of it as the cone of X over X, or maybe it's easier if you want to think of it as X cross 0, 1, where you want to collapse both the X cross 1 to a single point, and then X cross 0 to a different point. So the picture you should have in your mind is you collapse the bottom now, and so the top's been collapsed to a single point, and the bottom has been collapsed to another point. Is that good? Yeah, here. Does that help? Okay. Good. Okay. Question. What is the suspension of S0? Good. S0 is just 2 points. And what happens is you can think it gets crossed at an interval, but then the points on top get glued. So the top just ends up looking like this. And then this points at bottom get glued, so it looks like this. And what is that? That's just S1. And likewise, I think you can see that the suspension of S1 is just S2. And you continue this way, the suspension of SM is just SM plus 1. So this is like very nice notation. It's like the notation works out just the way you want it to, right? S times S to the M is S, yeah. Very, very nice notation. What I want to say is that this fact here is a special case of a more general fact. So proposition. Well, you think of this as just being the suspension of the space. So I claim that Hn of the suspension of some space is just isomorphic with Hn minus 1 of that space. And I claim it's the exact same argument as before. Like, you can just modify this. Like, what would be your xa and x over a now? Let's just modify this argument to prove it. So I'm trying to get this now to be initial space x and some suspension of x. So you tell me, what should my x, my a, and my, well, x is just x. Okay, that's not super interesting. Oh, no, it's not x. What are these? How do we get we want to end up with the suspension of x. We want to end up with the suspension of x. So how can we think of the suspension of x as a quotient of two spaces? Well, I'll just think of it as the cone of x quotiented out by a copy of x. Yeah, just like we said here. You have a cone, and you just quotient out by one copy of x. So if we think now about what these give us, it's really the exact same proof. You began with your a, which is x, and then your x is c of x. Okay, so this is very, very bad notation. X is c of x and a is x. This is horrible notation. That was really bad notation. Okay, but x gets included into c of x, which then gets quotiented out to be the cone of x, which gets quotiented out to be the suspension of x. X, the cone of x, the suspension of x. But what do you notice about the cone of x? Here's the cone of x. What do you notice about it? It's contractible. So the cone of x is, we study it precisely because it's a space you build to be contractible, because you have every point in x just going to this point. So you can just contract it along the cone. Right? You just move x up the cone till it gets to a point. So this is built to be contractible. Whatever x looks like, it doesn't have to be a circle. Whatever x looks like, you just move it up the cone and contracts to a single point. So all of these homologies of the cone are just 0. Okay, let's do a different color. Are just 0. And then just like before, you get the Hn of the suspension of x is isomorph to Hn minus 1 of x. Right? So the main application of this is for spheres, but it's a more general effect than just spheres. I want you to see this more general effect. Okay, what I want to do to wrap things up today is I want to talk about a really significant corollary of this theorem. So this is a corollary of our fact about spheres. So here's my corollary. Brouwer's fixed point theorem. Do you recall what Brouwer's fixed point theorem says? We proved it in the special setting of n equals 2. What we proved before is we proved that for any map from D2 to D2, and this is a continuous map. Everything in this class is continuous. So when I write a map, you assume it's continuous, but let me make it clear, because in other settings you might think this is not true if this is not continuous. So for every continuous map, for any continuous map, there exists a fixed point. There exists a fixed point. So there's some point x in D2 such that f of x equals x. We proved this in D2 before. What we're going to do today, to conclude, is show that it's true in general. Okay? So, nice little result here. Let me try to remind you of how we did the proof when we talked about the fundamental group. Do you remember? The key fact for the fundamental group is we said that if there is no fixed point, then there exists a deformation retraction. Do you remember this? Okay, so like let's think about the reasoning here. What's the deformation? Oh, so the deformation retraction is some map from, well, now it would be from dn to the boundary of dn. So like let's think about what this map looks like. Here's my dn. It looks suspicious like dd2. And suppose there are no fixed points. That means every point x gets sent to some point not x for f of x. F of x is never equal to x. But then we said what you can do is you can draw the ray from x through f of x until it hits the boundary, and now you've defined a function r of x. And think through, if f is continuous, this function is continuous. And this gives you a way to, x.
It's the way of drawing f of x to x that we would x.
Yes, yes, very good. You want it to be fixed on the boundary. You want it to be fixed on the boundary. This should be fixed on the boundary. Good catch. I was just worrying about that. Okay, so we have the ray go this way, so that if x is on the boundary, so, for x on the boundary of dn, we want that these points stay fixed. Okay, this isn't a deformation retraction. This is just a retraction, just a retract. But it could give you a way to deform as well. You just move each point x closer and closer and closer to that point on the boundary. But this r by himself is just a retraction, a retract. So now I have to move everything. So recall what a retract is. Hence, if you, so the definition of retract by design, if R with the inclusion map, so you still have an inclusion map. I that just includes the boundary of dn into dn. What this will be is this is exactly identity, right? This is exactly identity on the boundary of dn. Okay, so that's still true here. If there's no fixed point, you have a retract. And the composition of that retract with I gives you identity. But that can't be. But if you do have some retract that takes you from dn to the boundary of Dn, and then includes it back to Dn, such that the composition of the inclusion map with the retract is identity, then these all induce maps on homology. These induce maps on homology. And the composition of the induced maps is the induced map on the composition. So this should be the induced map on identity. And we talked about last lecture, the induced map on identity is just the identity map, right? So this is just the identity map. So you have the composition of these maps is just the identity map on your homology. But let's think about what this means. What's the homology of this guy?
I think you've got it switched around. It should be boundary of the should be your starting end, and your starting end.
Oh, I want to do the inclusion map first. What am I doing? I want to do the inclusion map first. Thank you. Wow, this is rubbish. I want to do the inclusion map first and then R, because it should be the map R composed with I that gives me identity. So this is the boundary of Dn. This is the induced map by inclusion. This is just Dn. And this is the boundary of Dn. And so this is the induced map of R composed with the induced map on I. Thank you. Very good. This is the induced map on the retract. This is the induced map on the inclusion. But what do you have here? This guy is just, well, this is S of n minus 1. Oh, this is also S of n minus 1. Right now those are 0, so let me change this. Let's make these n minus 1s. OK, there we go. Hn minus 1, let's make these n minus 1s. So now this comes out to be a copy of Z. This comes out to be a copy of Z. And this is 0. So we're saying that the identity map from Z to Z, the thing that sends 1 to 1, is equivalent to some composition of maps that takes everything to 0 and then includes, and then that 0 map somewhere. Like, this guy here has to take, your generator to 0, whereas this guy here is taking your generator to the generator. So this is impossible. This cannot be. So that's my contradiction. Thus, our assumption that there was no fixed point is false. So there must be a fixed point. So what a clever proof of Brouwer's fixed point theorem, right? It just follows immediately from the homology of spheres. OK, we're going to stop there, but in the upcoming weeks, we'll be talking a lot more about these exact sequences and learning to kind of diagram chase through them, doing some nice homological algebra. So that's what we're doing in the upcoming weeks.